So continuing on with our discussion, we'll next talk about the Malate shuttle. Now, I got confused with this when I looked it up in the book when I was going through Biochem 2. And there's a malate citrate shuttle and a malate aspartate shuttle. I want you guys to think of this as a malate aspartate shuttle. So to begin with, why are we doing this? Kind of the same reason as a glycerol phosphate shuttle. In anaerobic glycolysis, we need to keep our stores of NAD+ secure. And we do that when the reaction from pyruvate turning into lactate takes place. We're able to oxidize NADH into NAD+. Well, in the malate shuttle, we'll be able to do that, keep those stores of NAD+, but we need oxaloacetate in order to do that. So let's draw this. We'll imagine this as our cytosol. Right over here is our matrix. We'll have our inner mitochondrial membrane. And so let's start with oxaloacetate. Oxaloacetate, we said, is going to oxidize NADH into NAD+. And this will keep our stores of NAD+ fresh and supple, and the cytosol, which is what we want in order for glycolysis to keep on running. When we oxaloacetate will then turn into malate. And this reaction is uses the enzyme that's known as cytoplasmic malate dehydrogenase. Yeah, I'll write it in there for you. Cytoplasmic malate dehydrogenase. I hope you guys can see that. That's pretty squished in there. Anyway, so oxaloacetate in the cytosol. Wait, hold up a sec. I thought oxaloacetate was part of the citric acid cycle, and that was involved in the matrix of the mitochondria. You are correct. We need a method in order to ship out oxaloacetate into the cytosol in order to oxidize NADH into NAD+. And we'll just kind of go out of order, but we'll continue this order. So to be continued with that, but malate, using a protein transporter, can cross the inner mitochondrial membrane. And this exact opposite reaction will take place in the matrix. And we will be able to reduce NAD+ into NADH. And this enzyme that catalyzes this reaction is known as mitochondrial malate dehydrogenase. Right. And the next, continuing on, oxaloacetate, we will turn him into aspartate. Now when we do this, we need to use an enzyme, and that's known as aspartate transaminase. I'm just going to put AST, and that enzyme will convert glutamate into alpha-ketoglutarate. So that's glutamate, like a hey mate, into alpha-ketoglutarate. I'm not writing the whole thing because we're running out of space anyway. And as aspartate can then use another protein transporter and get to the cytosol, which we can then turn into oxaloacetate. Again, we're going to do the exact opposite of this. So we're going to get our alpha-ketoglutarate. I won't be able to fit everything in, and turn it into glutamate. And we're using the enzyme AST for that. Awesome. So let's talk about ATPs. So far, we're doing this 2 times every time glycolysis cycles through, and we're getting out 2 NADHs every time we go through this. So ATP value of NADH is 2.5. We multiply that by 2 because we need to undergo this process twice, and we'll get 5 ATP per 1 1 molecule of glucose. Now that's a little bit better than glycerol phosphate shuttle. Why don't we just use this all the time? Well, I'll tell you why. This can't be utilized everywhere. It can only be utilized in heart tissue or cardiac muscle, as well as hepatocytes or just liver cells. It's probably due to just the presence of these certain enzymes in these cells and not into other cells. But yeah, that's it for the Malate shuttle. One important thing that I would like to include is, you know, just maybe generally overall purpose of this would be to move reducing power across membrane. Move reducing power across the membrane. So we're moving this reducing power from NADH to NAD plus over all the way over here. Cool. Another thing to just keep in note, you know, let's talk about ATPs again. So from glycolysis, we get about 2. From PDH, we get about 5. From TCA, we get about 20. So right there, we have about 27. Now if we use glycerol phosphate, we're going to have about 3. And that'll get us 30. Or we can use malate. And if we use a malate, that'll give us 5. It's 3 or 5. I guess I shouldn't have put that divisible sign, but anyway, overall we'll be either getting 30 or 32 ATP. And that's just a rough estimate. You know, of course there's like heat loss that needs to be taken into consideration, temperature, pH, the partial pressure of gases, their overall atmospheric pressure. So take that with a grain of salt, like outside of the academic setting, but in this class, that's what we'll be saying. Awesome.